Hi everyone. This is the second part of lecture 4 for the chapter for optimal receiver for NTHU channel. The first part of this lecture 4 is about the optimal detection in presence of an uncertainty, and this video, today the second part of the lecture is about the detection of signaling scheme with memory. With memory, that means that we have the modulations that every symbol has a correlation with the past symbols. For example, we have discussed about the differential Dpsk, and that has correlation with one previous symbols, and we have discussed about the continuous phase modulations that has every symbol transmission has correlation with the previous phase, the phase, so all these are modulation with memory, and today we're going to talk about how to do the detection of signaling that with these types of modulations with memory. And we're going to have the two parts of have two topics on the detection. The first detection strategy is called maximum likelihood sequence detector, and it's different with a little different with the ML maximum likelihood detection, the symbol by symbol detection we have discussed in the for the memoryless modulations, that is symbol by symbol detection. And so with memory, every symbol is correlated with the past symbols. So we have a sequence of the transmission, and the detection would be based on a sequence of received signal and to detect a sequence of transmitted signal. So it is called maximum likelihood sequence detection. And here we're going to use the differential Dpsk as the example to discuss this maximum likelihood sequence detection. The second detection we're going to discuss is called optimum receiver for CMP. It's specifically for the continuous phase modulations that we have discussed in the chapter 3. Okay, so let's begin the discussion. Let's have the MLSD first. Okay, the maximum likelihood sequence detection, and as we know, the modulation with memory, that means that the signaling can be represented by the trellis, right? The trellis of the transmitted sequence, right? Every given a sequence of transmitted symbols that corresponds to a path in the trellis. Trellis means that all the possible transmission sequence, and the received sequence, or the transmit sequence and the received sequence would correspond to one of the paths in the trellis. Okay, so now if we assume the transmitted sequence of K symbols, we have a sequence of K symbols, and and supposedly the receiver would receive K symbols, right? The receiver will also receive the K symbols, right? And so this so we have K symbols transmitted and we have K symbols received, right? And every symbol is not independent, right? So this the sequence is denoted by this small k here, okay? And so the K sequence, we have to compare all the possible combination of the sequence, all the possible combination of the sequence, and with the received sequence, okay, and then compare the distance between the received sequence and all the candidate sequence. Okay, so this is called maximum likelihood sequence detection. It's the sequence to, instead of symbol to symbol comparison of distance, that compare the sequence to sequence comparison of distance, right? So all the possible, the distance of all the possible paths in the trellis and compare with the received sequence, and find, and then we make a decision from the trellis, in the trellis, that then decide which sequence in the trellis has the minimum distance with the received sequence. So this is called maximum likelihood sequence detection. As we can see that the computation would be complicated, right? Because there are m symbol in the sequence. In the sequence, there are k symbols, right? There are k symbols, and each symbol is a m array modulation, right? So the computation would have to go through the m array modulation and over a length of k sequence. So the computation, the complexity would be order m to the order of k, right? So it's very complicated, right? In general, this kind of detection is very complicated, okay? So the strategy to reduce the complexity has been, many strategies has been proposed, like a viterbi detection and so on. So here let's use the example that we have previously discussed. Is called differential Psk as the example to illustrate the MLSD detection. Let's have a review of the Dpsk first. Okay, what is differential Psk? The differential Psk that we have, the timing diagram that we have, the original binary message is AK, for example, okay, and AK is 0 or 1 because it is binary. Okay, so AK is 0 or 1, and we have a sequence of the message for transmission. And the differential encoding that we have, BK, okay, BK is an encoding, okay, differential encoding based on the input AK and the previous symbol, right? A previous symbol, okay, and this previous symbol BK minus 1 would again is correlated to the previous BK minus 2, and BK minus 2 is one step correlated to BK minus 3, and so on, right? So every symbol BK is correlated to the previous symbol BK minus 1, okay, and in combination with the current input AK. And so that here this differential encoding means that the BK would have a transition whenever there's one in message one comes in, right? Whenever there's a message one comes in, then the BK would have a transition. And when the input is 0, then BK remain unchanged. And whenever there's 1 and the message 1, right, then BK would have a transition, right? And there's 1 and BK has a transition, and there's 1, BK has another transition, okay? So it's differential encoding that BK represent every the transition whenever there's a 1 in the message, then BK would toggle. BK has a transition. Okay, that is the encoding strategy. Okay, and however, so obvious, and then BK is the transmitted symbol, right? BK is still binary, it's 0 or 1. Then it's a mapping to plus and minus signaling, okay, of SI. This BK is 0 or 1, and then BK is mapped to the to this plus and minus signaling, antipodal signaling, and then is then have this signal on the carrier, cosine carrier, and then we have this SIT. Okay, so what is really transmitted is BK. Now BK, the toggling of BK is the message that is transmitted, and we can see that BK has a memory, right? BK has a memory with the previous symbol. Okay, so BK toggle whenever have AK is 1. So in the in the output of the transmitter, in the transmit waveform is SIT, right? Over the carrier we have this SIT, and so SIT would have a phase change. We can see that the waveform BK will represent the baseband waveform, right? And SIT will represent the passband waveform. And whenever there's a transition toggle in BK, and then the transmit waveform would have a phase change from -1 to +1, or from +1 to -1. Now, whenever there's a whenever the waveform has a transition, that means that there's a toggle in BK. Okay, so that would be the overall signal scheme for differential Dpsk, and so obviously we cannot detect the message by BK symbol by symbol, right? We have to detect the BK that based on a combination of a sequence. Okay, so so based on this scheme, that we can have the obtain the trellis of the trellis of the transmission of the signal SIT. We could obtain a trellis. So that's have the S0 and S1 represent the state in the trellis, the state of trellis, and the state is represented by the value of BK. If BK is 0, then we say this the transmission is in the state 0, and BK is 1, we say the transmission is in state 1. And whenever there's input of the message AK, then AK would change the would give the output of a new transmission symbol VK, and that BK will represent the new state of the transmission for every transmission symbol. Okay, so in here, so we can have the transmission sequence based on for a Trellis diagram. That Trellis diagram gives all the possible passes. Say if we from say the t time is 0, then we begin with the it could begin, the state could be S0 or could be S1, and the S0, that the state 0, that means this BK is 0, and then when there's input of 0, then the next state would be remain S0. When there input of 1, then the state would transition to S1. And similarly, when the previous state is S1 and the incoming is 0, then the state remain unchanged. And when the incoming is 1, then the state would toggle. Okay, so from time to time, from symbol to symbol, whenever there's a 1, then the state would toggle. When there's input of 0, and the state would remain unchanged. Okay, and then it continues on this transmission that every time, every symbol, when there's 1, then the BK would toggle, and when the AK is 0, then BK remain unchanged, and so on. So in this Trellis diagram, that in here, for example, this shows 4 symbols of transmission, right? And all the possible paths in the transmission sequence, we can find paths. We can find a transmission paths that correspond to every transmission sequence of the symbol. Either the transmission sequence of AK, right? That we can, for AK, we can find a path, or for that corresponds to 4 different BK, that can find the path on the trellis. We can also represent this behavior by the state diagram, as we have described. We have state we have state 0 and we have state 1, right? And whenever there's a 0 of message, the message 0 comes in, then the state would remain unchanged. The state will remain unchanged whenever the input is 0. And when the input is 1, then the state would have a transition, right? We have a state transition whenever there's the input is 1. Okay, and if we assume the initial state, okay, initial state at t equal to 0 is S0, for example. Okay, that's for example, say the input is S0, and then we define the distance matrix. Okay, by for the information bit, on the previous information bit, there's information bit at k-1, information bit at k-2, and SI represent the current state. Okay, and make a decision. So at t and at here at t equal to 2t, at t equal to 2t, they are the path entering S0, t equal to t, the path entering to 0, right? Entering to state S0 here, that begin with S0 and end with S0. There are how many possible paths? There are 2 possible paths. This blue path here from S0 to S0, and this red path from S0 to S0, right? So there are two pairs. That is 0, 0. There's a 0, 0 of AK or 1 and 1, right, for the AK. There are two possible paths, blue line and red line. And so in this blue line and this red line, you can select one survival path. Okay, we select one survival path. That the survival path means that the distance, okay, the distance, okay, the distance of this path and the distance of this path, that find the path that has the minimum distance that represent that is the survival path. Okay, and okay, that's the one of the survival paths. Also, at t equal to 2t, that entering S1 here, right? Entering S1 here, that begin with S0 but ending with S1. And then how many possible paths? Again, there is two possible paths, right? It's 0, 1, right? And 1 and 0 of AK, right? There are two possible paths. The AK 0, 0 and 1, and 1 and 0. Okay, again, there's two possible paths. Okay, so S0, there are two possible paths, and S1, entering S0, there are two possible paths, and entering S1, there are two possible paths. So among these two, we select one as survival path, and among these two, we select one as the survival path. Okay, and instead of keeping all the four paths, that at every symbol we keep just one survival path entering S0 and one survival path entering S1. And this survival path information is passed down to the next symbol transmission, okay, and then help to decide the next symbol. Okay, now we have the suppose that we have the find out the survival path. Okay, find out the survival path that at t equal to 2t. We have find the survival path for S0 and for S1. We have survival path, and the survival path is this. Okay, the previous survival paths are to the S0 is this blue path is the survival path for S0, and this red path is the survival path for S1, right? Okay, so that is the two survival paths that associate with S0 and S1. And if we continue to transmit the third symbol and receive the third symbol of R3, and then the third symbol that could be entering could be S0 or could be S1, right? And there are two paths from here. There are two paths, right? There are two paths that entering S0. And there are two paths entering S1, right? So among these two paths, that we would select one path, one out of two. Okay, either this previous survival path and this path, and this previous survival path and this path. So the length of 3 and these two paths would we select one survival path for the when for the third receive symbol. Okay, so say we select one survival path that entering S0 for the third symbol. Okay, that is the accumulated path distance. And similarly, we select one survival path that entering S1 here, right? And is by the accumulation of previous survival paths and the and accumulate the two possible new paths, right? Then we have the two candidates for entering S1. And from these two paths, that again we select one survival path for S1. Okay, so every new symbols coming, we keep selecting one survival path, okay, for S0 and one survival path for S1. Okay, in this way we have sliding is like sliding window processing of the all the possible paths. So at each stage, when we continue to process the we have processed the coming transmission and the receiving signals at t equal to kt. We keep processing we keep two survival paths for S0 and S1 respectively, and then entering the next stage. And so that we can leverage on the previous survival path to find the maximum likelihood sequence detection result. So instead of compare all the possible paths at the end, when we collect k symbols and compare all the combination of the paths, we can use this survival path strategy to reduce the computation cost. Okay, so its decision of the path has to depends on memory, and this process when each new signal samples is received, then we could have a very quick decision of the new survival path, and then from the survival path we can have a decision of path. And this way, okay, this survival path and strategy is called the Viterbi algorithm. Okay, so we can see that the detection has to it's not symbol by symbol, but has to based on the information of the previous symbols. Okay. So next we're going to talk about the optimum receiver for CPM signals. The CPM is the continuous phase modulation signals. Suppose we have this continuous phase modulations. For example, that we have the continuous phase FSK. Say this is the signal for the continuous phase signal, that ST, and there's a phase phi t. I is the vector I is the sequence of the previously transmitted sequence, right? So the phase phi, that would be represent the accumulated phase, so that the phase could be continuous. Okay, for the carrier phase of the CPM, the phase trellis is remember the phase trellis. Okay, the phase trellis of each symbol, that is the accumulation of the phase changes in the phase trellis, right? And and the phase change is by defined by all the possible sequence of the symbol ik, right? The possible transmission sequence ik, the till n, the symbol n that represent them, that defines the path of the trellis, and that defines the current phase, right? The current phase. And so the phase, right? The phi represent the continuous phase, and here this the phase could be there will be integer number of phase of the previous integer number of phase theta n, and the new phase accumulation of this symbol. And theta n will represent the initial phase of this symbol, and the theta n minus 1 would be represent the new phase changes due to the symbol in. And here's qt and gt, and gt represent the pulse. Okay, gt represent the pulse of the pulse shaping function of gt. And for example, the gt would be could be a rectangular pulse, and the length of gt could be different lengths of lt that could cover L symbols, L symbols, that is gt. And qt will represent the integral of g tau until the t. And so the qt become after lt, that qt become a constant, and before between 0 and lt, the qt is linear. Okay, and so after the finishing of the pulse, then we have the full accumulation of all the pulses. Here the modulation index h is t, as we said, is t times delta f, and is or 2fdt. Fd is the frequency deviation of MFSK. And this modulation index h is just a number, because it's time, the symbol time times the delta frequency, delta frequency, and so h would be fractional number, is m over p. Here m and p are relative prime integers, and the pulse shaping function L, the length of the pulse shaping function L could be just one pulse, the length of 1, L equal to 1, and L could be greater than 1 period. Okay, L could be 2, could be 3, could be multiple of the symbol time. When L equal to 1, we call this is full response CPM. Every time, every phase changes would finish within one symbol time. Okay, the response of the phase changes could finish within each symbol time. It's called full response, continuous phase modulation. And if the L greater than 1 period, the length of pulse is greater than 1 period, then it's called a partial response continuous phase modulation, because the phase trellis, the phase trellis is in every single time there's only part of the response show in in each period. The phase in the full response CPM, the phase trellis, the possible phase trellis has P or 2P phase state when M is even or odd. Okay, and we will explain this. And the phase trellis would have additional phase state due to the partial response of GT. Okay, the phase trellis, okay, for this L equal to 1, the full response CPM, how many possible phase state, okay, the number of phase state in the trellis, okay, is either P phase state is determined by this P, either P phase state or 2P phase state, and for this M is even or odd. Okay, why the phase state, the number of different phase, right? The number of different phase represent the phase state. There are P phase state or 2P phase state. Okay, it's because, for example, there's, for example, the for H equal to 2/3. Okay, for example, this say this is the H. Okay, the ratio of H is M equal to 2 and P equal to 3, and you can see that the number of phase, the possible phase state would be 2 pi over 3, right, or 4 pi over 3 and 6 pi over 3. Then we have 2 pi. We have 1 over 2 pi, and then we have a cycle. So then we have a total of 3 phase state. For H, then for another example that H equal to 1/2, then how many possible phase state we could have? We could have incremental, the phase change is pi HIN, right? Pi HIN. So the possible phase change will be pi over 2 and pi, and in incremental, okay, in incremental of half a pi, incremental of half a pi. Then we have, and after when we reach 2 pi, we have all the possible phase state here, right? This is incremental of 2/3 of pi, incremental of 2/3 of pi. And so how many phase state here? We have 4 state, right? 4 state is the 2P. And how many phase state here we have? We have 3 state, right? So that is P, right? So we have P state or 2P state. Depends on the M is odd or M is even. Okay? Okay, so also that's so it's actually depends on, it's the modulo of 2 pi over the H. The phase trellis of the MRA CPF-SK, for example, with the M equal to 4, the MRA CPF-SK. So because M equal to 4, the the continuous phase FS signal is generated based on the IN that contains 4 different symbols, plus, minus 1, and the plus minus 3. So every transmission, the IN equal to 4 different values that would be correspond to 4 different phases. Right, and 4 different phases, and in every new symbol transmission there will be generate another 4 different phase changes. Right, and and then we continue to send the signal. Then we will have the receive the continues to have the receive sequence, and all the possible combination of the transmit sequence would show on this phase trellis. So then we have a transmission, and then we would receive the symbol. We have received the symbol. Say this is the first received symbol that is after the first transmission. Okay, after the first transmission of the symbol, then we have a received signal. But the received signal R1, so is not exactly the same as any of the 4 possible candidates, right? It's not any of the 4 possible candidates. It may be closer. It's closest to one of the candidates. Okay, but we do not make a decision immediately, because the every symbol has a correlation with previous symbols. Then we continue to receive the sequence, and then we have the second received symbol, and then we have the third received symbol, and then we have the another new received symbol, and all the received symbol, because of the noise and because of the channel, and would be it's not likely to be exactly the same with the it's not likely to be on the phase state, right? Exactly on the phase state, right? And so then together we have phase trellis as this red dotted line, that we have received the signal path. However, this signal path is not likely to be identical with any of the candidate paths. Okay, then we so after we have the transmission of n transmission symbols, after we have n transmission symbols of S, and then every transmission symbol is a path, and every transmission symbol has a path. So the difference of received sequence are and to the each candidate together, that makes the overall path to path difference. Okay, the path to path difference, and the received sequence have a pairwise path difference with all the path candidate. Right, and what say this Sj is one of the path candidate, right? Say Sj is one of the path candidate, and Sj maybe select one of the in the path Sj, that it may be one of the at one time that is the very close symbol to the received symbol, but not all the symbol in the path SJT that is close to the received path. So one of the paths, okay, so among all the candidate paths, there would be one path, right? There will be one path that overall, in general, the accumulated path difference, right? The overall path, the path distance difference, the difference of path difference that has the minimum overall distance with the received sequence. Okay, overall maybe one locally the distance is not the best, it's not optimum, right? This blue line has a shorter distance with the received signal. This red line may have the longer distance with the received signal. However, if the overall this red path has the shortest difference with the received path, then we say this red path, this SJ, is the candidate of is the optimum decision of the path. Then we could correct the local error. The local error is corrected because of using the path-to-path comparison. Okay, then we will reach the decision by the phase trellis detection. And the state of the continuous phase signal at when we have t equal to nt may be expressed as a combined phase state and the correlative state as a vector. That's the state vector, okay, the state, okay, the state of the signal at t, the signal, the state of the signal have to be can be expressed by a vector. Okay, the signal when the time comes to t equal to nt, we have a sequence of received signal, and the state of the signal can be expressed by the state, and the state is determined by many parameters. Okay, the state of the signal is determined by the phase state, right? Or initial phase state, and all the previous transmission symbols, right? And so all this argument that determines the state, determine the state of the signal, and so we have we call this is a vector, state vector, okay, state vector. And the initial phase has two phases, and the previous symbols, every previous symbol is an M array modulation. So together we have lots of combinations to determine the state of the signal. So the number of state, okay, the numbers of the state at a signal, that it could be P, right? P is the number of phase state times M to the order of L minus 1, because we have L minus 1 previous symbols. Okay, L is the length. L is the length of the pulse. Okay, L is the length of pulse, and so we have so the number of state that there will be this many number of state. Okay, for example, for the full response, L equal to 1. right? L equal to 1, then this would be just in, theta n and the new symbol in determine the state of the new signal. Right, so the signal the state would be affected by the previous accumulated phase and the symbols within the pulse, the correlated symbols in the pulse shaping function. And if we continue to send a signal, we have a new symbol, then the state vector would advance one more symbol, and then it will be determined by theta, the new initial phase, and the new correlated symbols in the pulse. And let's discuss the performance of the CPM. Okay, now we have the strategy, the mechanism of making the detection of CPM, right? The pass-to-pass comparison. It's actually similar to the MAP detection strategy, but it just become from symbol to symbol comparison in the ML detection to pass comparison in the MLSD, right? Pass-to-pass comparison. So based on this comparison and the sequence detection scheme, and we can discuss the performance of the CPM. So that SIT and SJT, let's use the symbol notation on the textbook. You can also refer to the Perkins textbook for further reading of the overall material. Okay, so that SIT and SJT represent the trajectory after n transmissions. Okay, and so we have a signal after length of n sequence transmission and receiving, and then we have accumulated phase that is phi t I, and here the vector I represent the previous the transmission sequence. Okay, so the detection, the sequence, maximum likelihood sequence detection is based on the Euclidean distance between any two candidate, right? Any two candidate. Say SIT is one candidate in the Trellis path. SJT is another candidate in the Trellis path over the interval of NT. Okay, there's any two Trellis, and the distance between these two paths. Okay, the distance between these two paths is that is Dij. The distance, the square of the distance. Okay, the square of distance. That is that over the past time period of NT that we compare the distance, right? All the accumulated distance between these two paths, right? The accumulated paths over the interval of NT. And then we just by this just a simple math here. The uh, the first term is Si squared, and the last term is Sj squared. The power of Si and the power of Sj, the accumulated power of the path Si and accumulated power of the path Sj, and then the cross terms, right? And the cross terms of the path Si and Sj, right? Just do this simple math. And the suppose the energy, okay, the energy of the each symbol is Es, and after n transmission that is n times Es, and we have two sequence. So the overall energy is NES plus NES. That's 2 NES. And this cross term that we just have this here, right? We just have this SI, the signaling here SIT, and then and SJT, right? So this is SIT, right? And this cosine, phi, and sequence of the sequence I, and the cosine with the phase trajectory phi with sequence J, right? Sequence I and sequence J, right? And then just by simple the cosine times cosine, we have plus and minus of the argument, right? And the plus term would be 0 because of the average. Okay, only the difference term, right? The difference term of the cosine argument is that remains here. So here we have the remaining term is the cosine phi I minus phi j. Okay, the difference of the phase, and together with the distance, then we have so we have final representation of the distance. Okay, and let's denote this. Okay, over the ES is the simple energy, and EP is the bit energy, and let's denote this overall integral as the delta Ij. Okay, delta Ij represent this overall result of the integral. So, and the and here the phi epsilon. Okay, this is just all rewrite and re-express the distance, and epsilon represent the accumulated difference. Okay, accumulated difference of the vector I and the sequence I and the sequence J. Okay, and the sequence I and sequence J would give the overall phase, the phase difference. Okay, so now we have the this overall integration phase accumulation difference result as delta Ij, and the distance. Okay, the distance would be represented by the distance square, represented by 2 EB delta Ij squared, and so that the distance Dij between any two paths would be square root of 2e times delta Ij. That would be that represent the path between any distance between any two paths. Okay, and let's use this result to find the an error probability representation. Here I, okay, the sequence, the sequence I and sequence J, the symbol is M-array modulation, right? M-array PA modulations, and epsilon is the difference, right? Epsilon is the difference between the sequence I and sequence J. So every component would belong to the set of 0, plus minus 2, plus minus 4, and so on. And so it's not as complicated as it looks. The pairwise error probability between any two paths. Okay, the pairwise error probability and between any two phase trajectory. Okay, the minimum distance could be found by the minimum distance between any two paths, as we have learned from the previous pairwise symbol by symbol detection. So, and the pairwise distance would be this random variable, the path itself is a random variable. The distance is a random variable with zero mean and the variance of n sigma n squared because of the length of n, and the variance, this random variable, when this random variable is greater than half of the distance, then we have an error in judgment in the detection of the path, right? The accumulated path, if the error is greater than half of the distance, right, then we have an error detection, right? It's the same concepts, or it's all the same concept here, right? So don't be confused. It's just look a little bit complicated, but it's not really difficult. Okay, it's the same concept. So this pairwise error would be equal to Q, that half of the D minimum over the standard deviation of the noise, okay, of the noise of the noise of the path, right? So that makes the pairwise error probability. Then we have the say each symbol, say the variance is n0/2, and we have a length of n. That then we have the path variance will be n times the variance, right? And the distance Dij we already wrote in the previous page. The Dij that is represented by the square root of 2EB and the delta Ij squared. So we have representation. We have derived the pairwise error probability in terms of the Q function. Okay, and here the delta Ij is the distance. And the union error probability of this continuous phase modulation would then be depends on how many paths, the path-to-path distance that has the minimum distance. The number of paths that has the minimum distance, and each minimum distance pair that has the error probability of this Q function, right, is similar to the MRA QAM or MRA PAM, right? The number of minimum distance and time and times the error of the error that has the minimum distance. So that gives the union error bound, the union error probability for the CPM signal. For the CPM signal, it's just apply the same concepts. Okay, and so finally we have discussed the how to detect the CPM signal with the phase trellis. Based on compare the phase trellis, we can have a detection strategy with the path-to-path comparison, and we also have based on the same concepts, the minimum distance concept, that is based on the minimum distance between the paths, we can derive the union error probability for this CPM CPM detector based on the phase trellis. Okay, this concludes this lecture, and also this will be the end of this chapter 4. And so we have this a new homework 3, that covers this chapter 4. So you could have practice of the chapter 4 materials. So hope it will help you to prepare for the next midterm. And homework 3 will be due the next week, the Thursday, by 6:30 p.m. Again, please submit your homework to the TA at the EECS building, lab 611, 611. Then to submit, there will be a box. There will be a homework collecting drop box at 611 of the EECS building, and please have your homework there. And also for the student that is either in quarantine or you are not entering Taiwan yet, able to enter in Taiwan yet, for the international student, you can have a photocopy of your homework and submit it in eLearn or submit it to the TA, and we will collect your homework. Okay, thank you. And next week we will begin the chapter 6 on information theory.